Good morning all of you. So in the last few lectures we have been looking at various aspects of the quantum behavior of matter. The first aspect that we looked at was the wave nature of matter, which is the counterpart of the particle nature of light. So essentially between Planck and de Broglie we have established a kind of symmetry between what we classically call as particles and what we classically call as waves. So this whole entire phenomenon, this dichotomy is called wave-particle duality, and it played a very important and a crucial role in the development of early quantum mechanics, the so-called old quantum mechanics, which involves Planck's radiation law, Einstein's photoelectric effect, and then you have Compton's scattering, Stokes anti-Stokes line, and then of course the Bohr model and de Broglie hypothesis. That is what we have. And after this there was a new understanding, a better understanding of all these phenomena in the language of quantum mechanics, which was accomplished by the work of Schrödinger and Heisenberg and also by Dirac, but that is not a subject matter for you, it is rather too advanced, and you will do that in your higher classes when you go for graduation. So what we have to now do is to come back to the Bohr model, which I had started discussing, and what Bohr essentially did was to make an extraordinary and a highly courageous hypothesis. That is a very important thing. It was very bold on his part because he was bringing in various concepts of classical electrodynamics and the quantum hypothesis together. It was there to a certain extent in Einstein and Planck, but it was certainly not as pronounced, as explicit, as clearly expressed as in the case of Bohr. And as I told you in the last lecture, for this reason Bohr is considered to be one of the deepest and the most profound philosopher scientists of the 20th century. He had an enormous influence. So let us recall what exactly Bohr did. So we had the problem of these spectral lines. So you see that here in this picture. So what we have is so what is it that we had? Classically the atom should not have existed at all, it should emit by continuous radiation, but that does not happen. Atom is completely stable, but however if you excite the atom it is not stable, only in the ground state there is a minimum energy state. As yet we do not know where that minimum energy comes from, even the Bohr model will not give you, but once we excite it again the atom will radiate, will come down to the ground state, will get de-excited by emission of radiation, but that again is not consistent with the Maxwellian prediction, because classical electrodynamics says the radiated energy should be continuous in frequency, in wavelength, or for that matter in energy. But here you see there is a very good spectrum, discrete lines, that is what we are seeing here. And we discussed at great length what the Lyman series were. These are in the invisible region, beyond the violet region. Then you have the Balmer series, which is in the visible region. Then you have Ritz, Paschen, Brackett, Pfund, etc., which are actually not in the visible region again, because they go to the invisible in the infrared region. That is what we got. And I also should remind you that all these spectral lines, the wavelengths, were collapsed into a single formula by Rydberg, and that is given here. He found that 1 over lambda is some mysterious constant multiplied by 1 over n1 squared minus 1 over n2 squared, where n1 and n2 are integers. Obviously n2 should be greater than or equal to greater than n1. That means the number, the quantum number n1 should correspond to the ground state of the system. N2, N3, N4, etc. should correspond to the excited states of the system. Rydberg constant, which is known to a remarkable accuracy, as I told you, almost up to 14-15 decimal places, was a phenomenological constant. It was determined experimentally, but the big question was, where does it come from? So these are the other lines, as I told you, the Lyman, the Balmer, and the Paschen. So you can see Paschen should be n1 equal to 3, I am sorry, and n2 should be 4, 5. Brackett corresponds to n1 equal to 4, Pfund corresponds to n1 equal to 5, this corresponds to 6 and this corresponds to 7, and this was discovered very recently, for which you need very precise and very well resolved spectroscopy. Okay. Now Bohr came and clarified the situation, although he did not completely solve the problem, by making two hypotheses. I will go through that very quickly so that we have continuity. The first statement that he made was that the orbits, the classical orbits in the case of hydrogen atom are all not continuous but discrete. Only some discrete orbits are allowed. When I say some, I do not mean finite, so let me remove this. Only discrete orbits are allowed. And what is the condition for the discrete orbit? And that is quantization of angular momentum. So what are we doing? We are assuming at the time being that the orbits are all circular. Therefore, we write m Vn Rn is equal to nh bar identically equal to nh by 2 pi. This is the condition. This is not unique to quantum mechanics. For example, if you look at the vibration of the string, you know that only some modes are allowed, and then of course the most general vibration is a linear combination of those modes. You have the fundamental, then you have the first harmonic, second harmonic, third harmonic, so on and so forth. In fact, this is not very different from that if you write down the equations of motion. So you already get an inkling that we are somehow importing the wave nature of particle. As I told you, historically the wave nature of particle came after Bohr proposed this model, but since we have already discussed the wave nature of particle, Davis and Germer experiment, so on and so forth, you can see that there is an inkling for this. So this you should compare with the modes of vibration. Right? So if you have a vibrating string, for example, with both the ends fixed, the fundamental mode is like this, then you have something like this, so on and so forth, and then you have the first octave, second octave, that is what they call it in music, and then what you will do is to look at all possible superpositions. This is something that you might like to revise, although it will not be immediately used. Analogy with vibrating strings. You can also have analogy with vibrating membranes, so on and so forth. Let us not get into that. So that was the hypothesis, and with this hypothesis Bohr was able to reproduce the mysterious Rydberg formula. I need to derive that formula again because I want to illustrate a large number of results starting from that, so that you people become completely familiar. These are what are called as scaling laws in a hydrogen atom. So let me repeat that. So derivation of the Bohr formula. Is what we have to write. So what is the Bohr formula now? There are two ingredients. MVn Rn is nh bar. Please remember h bar is h by 2 pi. Some people like to call h bar as the Dirac constant, but nobody uses it. And the second one is to assume circular orbits, and once the orbit is circular, what do we have? We have a centripetal force which is equivalent to the applied attractive force. So what are we writing? The centripetal force is given by mvn squared by Rn in the nth orbit, and this is equal to k over Rn squared, inverse squares law. And what is my k? My k is z e squared over 4 pi epsilon naught. Okay. By force of habit, we put this z, which is the atomic number of the nucleus, but for our purposes z equal to 1 because we are interested in the hydrogen atom. It is not easy to use this formula if you consider other atoms like helium or lithium or boron or beryllium or carbon, because there you have a large number of electrons and you will have to worry about the repulsion between the electrons. So for that reason, textbooks say these are hydrogenic atoms. So what you imagine is, if you take helium, you knock off one electron, so that it's almost like a hydrogen atom, except that the positive charge is now 2, because there are 2 protons, so on and so forth. So this Z should not be confused for the description of a real atom, where there are going to be Z electrons. We have to remember that. And these two equations give us the Bohr formula immediately. So what do? I bring this Rn squared here and multiply and divide by m. So I first do this, and then I bring Rn squared here. So this is brought here. Then what is going to happen? M squared Vn squared Rn squared is n squared h bar squared. So we are using the Bohr quantization condition over m Rn is equal to k. So we are asserting that the ratio n squared by Rn is a constant. That is the first consequence. So let me write that here. So n squared by Rn is equal to constant. So this is the first scaling law that we have. Or if you feel like, we can write Rn equal to n squared h bar squared over mk. That is what we have. So Rn varies like n squared. That is what we have. And this is something which is completely new in the Bohr model. You will not find it anywhere else. Okay. So I have got this beautiful result. Rn is equal to n squared h bar squared over mk. From this, I can immediately find out what my potential energy is. Now I have to be, of course, careful, because the potential energy is attractive. My proton is positive, my electron is negative, and there is an attractive potential between them. Therefore, my potential energy V, which is attractive, is given by minus k by Rn. So we are asking, what is the potential when the electron is at a distance Rn from the nucleus? By the way, when I am doing this calculation, you people should remember that I am assuming that the proton is infinitely heavy compared to the electron. It is 2000 times heavier. There is no problem about that. So if I plug in this expression, what am I going to get? I am going to get minus mk squared divided by n squared h bar squared. That is what you are going to get. So what happens is that as you keep on increasing the radius, the potential keeps on increasing. That is a very important point. The magnitude keeps decreasing, but then it is negative. Therefore, the potential keeps on increasing, and in the limit n going to infinity, it becomes 0. After all, that is how we defined our potential to be, k by r, it goes to 0. And therefore, if a particle is at infinity and it has some kinetic energy, the total energy is simply the kinetic energy. That is what we have. But our particle is not at infinity, because it is at a finite radius and it is going around in a circular orbit. So what we should now ask is, what is my kinetic energy? Kinetic energy is very easy to find. That is nothing but half m Vn squared. That is what we have. Now I need an expression for Vn squared. So what will I do? I will go back to Bohr and I will write m Vn Rn is equal to nh bar. So if I remember that, I need this expression in some point. So my Vn squared will be n squared h bar squared over m squared Rn squared. So this quantity is half m n squared h bar squared m squared Rn squared. Please don't be under the impression that my kinetic energy keeps on increasing as I go farther and farther away. That is not what is happening. What happens is that I have to substitute for Rn squared. So let me write that again here. My kinetic energy Tn is half m n squared h bar squared over m squared. I will simplify it, and I have 1 over Rn squared. So I need the expression for Rn squared. So that quantity will be m squared k squared. We have to pay good attention to everything, n to the power of 4 h bar to the power of 4. So, now we have the full expression. So, if I were to substitute and simplify, what am I going to get? This m squared and this m squared cancels. So, n squared, this becomes 1 over n squared to the power of 4, this becomes 1 over h bar squared. So, I am going to get half m k squared, I hope I am doing the right calculation, n squared h bar squared. This is my Tn. So, I am doing the calculation as I am teaching you, so you people should also work it out. So, now what we have to ask is, excellent, but what was my potential energy? If you look at it, my potential energy was actually minus mk squared over n squared h bar squared. So, what are we saying? We are saying the magnitude of the potential energy is twice the magnitude of the kinetic energy, and therefore, my total energy is a negative quantity as it ought to be. If my total energy is positive, you know from classical mechanics or classical even electricity and magnetism, the particle would be free to go to infinity, it will not be in a bound state, therefore, the total energy should be negative, and from these two I will write En is equal to minus half m k squared over n squared h bar squared. So, we got the Rydberg formula from this by making use of the fact that when there is an emission, then the energy carried by the radiation is nothing but the difference between the two energies multiplied by h nu, whatever nu, that is the energy. Therefore, you could get the frequency and therefore, you could get the wavelength. I am not going to get into that. So, what are we going to find? That is a very, very important thing. So, let me collect all the results. Let me collect all the results. The first one is that Rn behaves like n squared. That is a very, very important thing. Whereas Vn behaves like 1 over n. My kinetic energy and potential energy both behave like 1 over n squared. Therefore, my energy also goes like 1 over n squared. This is the origin of the Rydberg law, and very, very importantly, my Tn is minus half Vn. My Tn is minus half Vn. It is only half of Vn with the opposite sign. Therefore, my En less than 0 for all n. So, when I was showing you that list, Hund, Humphreys, etc., basically they were accessing very, very large values of n. That means the emitted wavelengths were very, very large, and therefore, it went into the deep infrared regime, and these are called scaling laws. These are called scaling laws, and from these you can derive a number of conditions without even completely solving the problem. You do not have to go, please remember this, because these are also typically the questions that are asked of you in your examination. So, this is something very interesting about the Bohr model. Now, every model needs a confirmation, because a model is proposed to understand one particular system. So, let us ask, how realistic is the Bohr model? You should not think that because Bohr was able to reproduce the Rydberg constant, was able to give the spectral lines, etc., it is sacrosanct and everything is great. What we should be able to do is to test it in a different system. So, what is the method? Method of testing, method of answering that question is to test the model in a different settings. in a different setting. And if the model fares well, then we can believe. If it doesn't fare well, it is not going to believe. So what we are going to do is to look at two examples. The first one is the celebrated Franck-Hertz experiment, and the second one is vibrational states of molecules. These two examples have a lot of lessons for us apart from giving us some numbers. So what we will do is to proceed slowly and try to understand. Franck and Hertz performed this experiment immediately after Bohr proposed this model. Bohr model came in 1913 and the first experiment of Franck and Hertz were reported in 1914, the Franck-Hertz experiment. And what was the experiment? Let me discuss that. So what Franck and Hertz did was to look at a completely different element, namely mercury. The chemical symbol is Hg. That is what they did. Because people knew what the spectral lines of mercury were. Now we should remember that mercury is a metal, so it is sitting somewhere far away in the periodic table, far away from the hydrogen atom, and mercury has a large number of electrons, whereas the Bohr formula is valid only for the single electron in the field of a nucleus. So what I want to tell you is, in spite of the fact that the Franck-Hertz experiment was hailed as one of the most beautiful experiments that verified the Bohr hypothesis, because soon after Franck and Hertz performed their experiment, Bohr himself wrote a paper saying that it is consistent with his model, and at some point Einstein is said to have remarked that this experiment is so beautiful it makes one feel weep with joy. Okay, that means this is an experiment which has had a tremendous impact on the psyche of the physicists those days. Of course, it is a beautiful experiment, but still we should remember the applicability of the Franck-Hertz result is not straightforward to the Bohr model. Therefore, it is bound to be qualitative and not quantitative. That is something that you have to remember. That was the state of affairs in 1914-1915. They were the 2 years in which Franck and Hertz did their experiment, and in another 10 or 12 years they had been decorated with a Nobel Prize, and no wonder about that, because this is one of the most beautiful experiments. So what is this experiment? So what you do is to look at the mercury vapor. So in a discharge tube, people knew that when the mercury is vapor, when the mercury is heated, then obviously the mercury atoms are going to get excited, the electron is going to excite it. So in discharge tubes, I could have brought a picture for that, anyway, never mind. There is one vacuum tube. Mercury emitted radiation of about, if I remember correctly, 250 nanometers. And this was a sharp line. That is something that we have to remember. This was known experimentally prior to Franck and Hertz adventure into this area. So now we have to make use of it and we have to see what can be done. So what is it that we did? What Franck and Hertz did was to look at took a look at a vacuum tube. So a picture of the vacuum tube is here, and if you people are going to your lab, you people can realize the anode, and then there is a grid here, and then there is a cathode. Basically what you do is to send cathode rays, which are nothing but electrons, and accelerate them or look at their motion. That is what you want to do. So what Franck and Hertz did was, take a small quantity of mercury. It was in the vacuum tube. And evaporate. This is very, very important. So what you do is to essentially produce a low density mercury vapor in the vacuum tube. And where is the mercury vapor? It is distributed all over the vacuum tube, distributed all over. This is very important for us, because this is the counterpart of the Rutherford experiment, where the target was a very, very thin foil. So when the target was a very, very thin foil, I argued that each alpha particle could have undergone at most one collision. That is the statement that I made. But then if the target is distributed over a certain volume in space, then you cannot make such an assumption. And indeed, Franck-Hertz experiment actually gives teeth to it, that we should not make such an assumption. Okay. So before I come to that, what did they do? They injected accelerated electrons. This is a simplified description in the tube. Now we have to know what the range of these energies were. So this energy range, this is very, very important for us, was a fraction of an EV to about 80 electron volts. So let us say 1 electron volt to 80 electron volts. That is what they did. Again, we are going to assume that mercury being a very heavy object, mercury nucleus being very, very heavy, we are now going to look upon mercury as what? We are going to now look upon mercury as infinitely heavy object. The Rutherford experiment had the alpha particle energy in the range of MeV, million electron volt. Here we are speaking of 1 to 80 electron volt, therefore the energies are 10 to the power of 5 to 10 to the power of 6 smaller than the alpha particle energy. And at this energy, we already know from the Bohr theory which I wrote, the ionization energy is 13.6 electron volts, so on and so forth. Therefore, electron volt is the characteristic energy for an atom. Therefore, my electron will not be able to reach the nucleus at all. It will get repelled by the other electrons in the mercury atom and it should get scattered. That is the idea. So this is the contrast between the Rutherford experiment and the Franck-Hertz experiment. So the cathode ray particles and their electrons interact, that is the most important thing, with the electrons in mercury atom. But the only problem is, if the Bohr hypothesis is correct, my electron cannot take the energy from the incoming electron. My electron in the atom cannot take the energy from the incoming electron unless it matches with the energy level description. So what are we going to write? So let us say this is my ground state energy of the mercury atom. Then you have the first excited state, second excited state, so on and so forth. We don't know what the spacing is. So let us say this is E1. So with the minimum energy that should be carried by the incoming electron is E1 minus Eg, if it has to go up. If the energy of the incoming electron is less than that, then the whole atom scatters elastically because you are not able to excite. What is happening? When you excite, the kinetic energy of the incoming electron will be converted into the internal energy of the atom because it is getting excited. But then what we are going to assume, or what we have assumed, is that the atom is infinitely heavy. So in that elastic scattering, if you look at the scattered electron, its momentum may change, but its energy will not change. It is like a ball going and hitting a brick wall. Okay, the momentum will change. Some momentum will be transferred to the wall, but no energy will be transferred to the wall. Therefore, the scattered electron from the cathode ray tube will carry the same energy. That is the principle. So here is a very, very beautiful experiment of the scattered electrons by mercury. I am going to look at it in great detail. So these are the incoming energies, and I know as soon as the incoming energy hit 4.9 electron volts, it immediately dropped. So what you do, you keep on sending energies of different energies, but as soon as it hits 4.9 electron volt, that is the magic number for me, it immediately comes down here. And then what happens, if I continue to accelerate, it will keep on going. As soon as it hits 9.8 electron volt, which is exactly twice 4.9 electron volt, again there is a sudden drop, and sudden drop to actually close to 4.9 it should be, but never mind about that. And again it will keep on going when it hits the energy 3.9. This is the most beautiful curve that is taken directly from the Franck-Hertz experiment, and we should understand that. So what we are saying is that there is this atom, mercury atom, there is this electron here, and there is this excited state here. So there is an electron here, and there is an incoming electron here. That is what is happening. Now this energy difference is 4.9 electron volt. So if the incoming energy is less than 4.9 electron volt, the electron will simply get scattered, its momentum will change, its energy will not change. So it will keep on going, and the incoming energy will be the same as the outgoing energy. The direction may be different, but you are not sensitive to the direction. Like in photoelectric effect, you are not sensitive to the direction of the emitted photon, you only gathered its energy. So in that way, it actually bears a good resemblance to photoelectric effect. But if the electron has an energy of 4.9 electron volt, now this is the cathode ray. This is the cathode ray. The electron in the atom can absorb all the kinetic energy and can come to this state, because the difference is 4.9 electron volt. So energy of scattered electron is 0. Now the question is, what is the cathode energy range? Cathode electron energy is 7 electron volts. No problem. You make use of the conservation of energy. So the electron will take 4.9 electron volts, and the scattered electron will have an energy of what? 7 minus 4.9, which is 2.1 electron volt. And if you look at this picture, that is what is happening. It is not becoming 0, okay, except the one which is at 4.9. The energy keeps decreasing. Now this 2.1 electron volt electron, as it is propagating in the vapor, it does not have energy to ionize the mercury atom further, and it will be detected as a 2.1 electron volt electron. Okay. Now what I will do, I will say that the incoming energy is, let us say, 9.8 electron volt. Now what happens? In the first collision, it loses 4.9 electron volt, continues with a kinetic energy 4.9 electron volts. But then it is moving through the bulk, it is moving through a gas. Another atom takes away the energy, and the final electron has 0 kinetic energy. That is what we are writing. So now that means that instead of 9.8 electron volt, if it had an energy of 10.8 electron volt, incidental energy, then final energy is 10.8 minus 9.8, which is 1.0 electron volt. Again, it is not enough to excite the atom further, therefore it will simply keep on getting elastically scattered, its momentum may change, but the energy will not change. And here you see there are 3 such peaks corresponding to 4.9, 9.8 and 4.9 into 4.9 into 3, that will be 3 9s are 27, 3 4s are 12, 14.7 electron volt. In fact, this last number is 15 electron volt, this is 14.7 electron volt. I do not know if you people can see this or not, but take my word for it, this is one of the most beautiful demonstrations. Of course, Franck and Hertz did not stop there. As I told you, they went all the way from 0 to 80 electron volt. You see a number of peaks, and these correspond to various various scatterings and various excitations, and this gave a great qualitative evidence for the Bohr model, because the Franck-Hertz experiment cannot be understood if the energy levels are continuous. So, although at this particular instant of time I do not know how to work out the energy levels of a mercury atom, for that matter I do not even know how to work out the energy levels of a helium atom, this gives a qualitative evidence. Franck and Hertz did something else. They waited, you do not have to wait for long, and they found that the excited atom is going to come down, excited vapor emits light of energy 4.9 electron volt. That is the most beautiful thing. It emits light prominently in the 4.9 electron volt. So, that gives another good evidence. And now, if you today look at the spectroscopic data, this is very well understood. You will see that these are the spectral lines. This is what corresponds to about 252 nanometers, exactly corresponding to 4.9 electron volt. Therefore, by hindsight, with hindsight we can say that Franck-Hertz experiment was one of the most spectacular and beautiful confirmations of the Bohr model. In 1914 or 1915 it was a qualitative confirmation. Today it is a quantitative confirmation, because these things are very well measured. If you go to higher studies, then you may end up doing an experiment on Franck-Hertz. There are many universities and institutions where it is done all over the world, including our country. So, what are modern day experiments? Modern day experiments. People do not use mercury, but people use neon. Neon does not have to be evaporated, neon is already a gas. So, they fill the vacuum tube with that, there will be some pressure, that is quite a small pressure. If you go and look up the paper of Franck and Hertz, you will get the complete data. And now again you scatter neon atoms of the electron. The beauty of this is that the energy gap is much smaller, and therefore emitted radiation is in the visible range. Whereas 252 nanometers is not in the visible range. That is the statement that we want to make. And I want to show you a picture of such a thing. This is a beautiful picture of what is happening in the vacuum tube. It is actually in the orange region, and you see this orange hue. So, not only do you make a measurement, but you can actually see with your own eyes that the radiation is being emitted in this particular region. Therefore, if you get an opportunity to perform such an experiment, you should not miss a chance, because in that case you would be essentially recreating one of the greatest experiments of the 20th century. The original paper is written in German, but I would still advise you to go through that, because again at least look at the equations and you can look at the graphs, and those of you who are studying German language would also enjoy reading that in the original, and I am sure it is very beautifully written. So, this gives you a confirmation of the Bohr model, but we want a confirmation in an even more quantitative way, and for that what we shall do is to look at vibrating molecules. This requires a little bit of preparation, but we are not in a hurry, so let us start with that. So, the basic idea behind this analysis, and which is universal, in fact it is ubiquitous, and you see the same thing occurring in molecular physics, the same thing occurring in atomic physics, the same thing occurring in nuclear physics, in fact even in quark physics. If you imagine that proton is made up of quarks, people will look at these vibrational molecules. So, what is the idea? Now, suppose you are given a potential which is very complicated, let us say something like this. This is quite different from the hydrogen atom potential that I wrote, because I am interested in atom or molecule. So, this is my potential and this is my separation. Now, what happens if two atoms come very close to each other? The electrons in one atom will start repelling the electrons in the other atom. If you want, you can even bring in Pauli exclusion principle. The electrons cannot occupy the same space. So, very close to the origin, the potential rises very rapidly. But the atoms are neutral, therefore, if you go far away, you should fall off very rapidly. So, it comes here and it will fall off very rapidly. In fact, we can arrange it such that it is going to 0 here. Is that okay? This is not a very good picture. I am sorry, because it is giving a misleading interpretation picture. So, the correct picture should be something like this comes here and falls off very rapidly and it will go to 0. So, if you take the derivative, or you can see it from this is repulsive here, it is attractive here, it continues to remain attractive but becomes very weak as you go farther and farther away in R, and there is a minima which is located at capital R. So, one very good example is the van der Waals force. I think it will look like A 1 r to the power of 6 minus B r to the power of 7, where A and B are positive constants. If you plot that, this is how it is going to look. This is nice. Now, what we will do is to not try to apply the Bohr model to this directly, because I do not even know the form of the potential, but I assume that whatever is bound here, the two atoms are here, they are very close to equilibrium position, At equilibrium position, it has the minimum energy. So, we are looking at small perturbations or low level excitations. That is what I want to do, whether it is classical or quantum mechanical. So, what are we going to do? We are going to say that V of R has a vanishing derivative at R equal to R. This is the equilibrium separation, let us say, between the two atoms, and which is a minima. Position for minima. What do I mean by that? All these are important. Minima means that del squared B by del R squared at R equal to R is greater than 0. So, these are the conditions that I have. So, I am sitting in the minima, and the way I have written this picture, this minima is a global minima, there is no other minima actually. Okay. Now, if that be the case, I can make a Taylor expansion of V of R around R equal to R. So, if I write del squared V by del R squared at R equal to R equal to K greater than 0, the first derivative is vanishing, therefore, my V of R in the immediate neighborhood of R will be capital R equilibrium V plus half k into r minus r whole squared. It is not the end of the thing, plus higher order. You do not have to worry about that. So, if I am looking at the separation, let me call it as some rho which is r minus r, mod r minus r. My potential is essentially some constant plus half k rho squared. And all of you without an exception will recognize this to be the harmonic oscillator potential. So, this should be a capital K, the way I have written, and your K, the spring constant, is nothing but the second derivative of the potential at the minima. So, what are we saying? Mathematically speaking, what we are saying is that wherever the derivative is 0 and the second derivative is positive, you can approximate the function in the neighborhood excellently by a parabola. That is all what we are saying. Of course, if it is a maxima, it will be approximated excellently by an inverted parabola. It will become a minus half k r squared. That would be a position of unstable equilibrium, whereas this is a position of stable equilibrium. Whatever we have written here, this is a position of stable equilibrium, and that is all what we have to worry about. So, now what we are claiming is that when two atoms come close to each other, if I model it by that kind of a potential, if I model it by this kind of a potential R, then if it is described by a quantum phenomenon, then the energy levels, the quantized energy levels must be given by what? The Bohr orbit rule to harmonic oscillator. So, what are we saying? Apply the Bohr model hypothesis to simple harmonic oscillator. Let us call it SHO. And what I am going to do in the next 10 minutes is to work it out. It is in fact even simpler than the hydrogen atom one. Actually, maybe it is as easy as that, and let us see how we are going to get that. Again, we shall assume circular orbits, and if you people feel like, you can even work it out in one dimension. So, my total energy E is given by half m v squared plus half k x squared. That is what I have. So, it is convenient to work not in units of k, but in units of the angular frequency. Therefore, we will write it as half m v squared plus half m omega squared x squared. So, everybody knows what omega squared is. Omega squared is k by m, because this is a natural unit. That is what we have. What is my force? My force is, oh, I am sorry, I should write it as a position vector. Let me take a different sheet. My E is half m v squared in 3 dimensions is what I am going to write, plus half k r squared, which is identically equal to half m v squared, I can put a vector sign here also, plus half m omega squared r squared. So, it is an isotropic oscillator. That is what we are saying. So, you display it in any direction from the equilibrium position, it will be pulled back in the same way. And what is the same way? My f is therefore given by minus k r. So, this is Hooke's law in 3 dimensions. So, you people have studied the oscillation in 2 dimensions, oscillation in 3 dimensions, Lissajous figures, how you get ellipses, so on and so forth. So, what I will simply do is to plug this equation make use of the Bohr hypothesis and see what is it. So, we are going to assume again circular orbits plus Bohr quantization. Is what we are going to assume. So, circular orbit means mv squared by r is equal to minus kr. All the directions are taken care of. The force is radially inwards, it is a centripetal force, and that is what we have written here. So, is also equal to minus m omega square r. Let us write both of them. And the Bohr quantization condition is, as always, irrespective of what the potential is, n h bar. So, that is what we are going to get. And again, we have to combine these two and we have to get a meaningful equation. What is the solution? There are many ways of doing this. One thing that we can do, so I am going to put a n and a n and a n here. I should not put a plus sign here because the signs are taken care of. There is no question of, because this is for the magnitude. So, what we have is that m Vn squared by Rn squared is equal to constant. And from the second equation, my Vn is equal to nh bar over mRn. So, that is what I have to use. Therefore, my Vn squared is n squared h bar squared over m squared Rn squared. There may be many ways of doing it, even more elegant ones, but never mind on that. Therefore, m Vn squared over Rn squared is what I am going to look at, is nothing but m n squared h bar squared over m squared Rn squared. That is what I have. Okay, I have to divide it by 1 over Rn squared. This is constant. I hope I have done the calculation correctly. Otherwise, we will have to repeat the calculation. Is equal to k. I think I am doing well. Therefore, we get the condition Rn to the power of 4 is, I have to simplify this, n squared h bar squared over mk. And this k is m omega squared. Therefore, this is n squared h bar squared over m squared omega squared. So, I got a relation Rn to the power of 4 is n squared h bar squared over m squared omega squared. I am interested in Rn squared because it is the potential energy. Rn squared is n h bar over m omega. So, this is a very important result for me because we are seeing quantum mechanics, rather Bohr model is giving a new length scale. In fact, the same thing happens even in the case of the hydrogen atom, which was your Bohr model for your Bohr radius, 0.5 angstroms actually. So, You notice that Rn squared is proportional to n. This implies my potential is proportional to n. There my potential was proportional to 1 over n squared, here it is proportional to n. In the next lecture I am going to show you that kinetic energy is also proportional to n, the total energy is proportional to n, and therefore unlike the hydrogen atom, where the lines were all getting bunched up as you kept on moving and farther and away because 1 over n squared, here the energy levels will all be equally spaced, and what we will do is to look for the experimental evidence in your atomic spectroscopy. The experimental evidence has to be carefully interpreted because the spectral lines are quite complicated, but I will tell you, and after concluding this in the next lecture, which should take us about 15-20 minutes, we will proceed to discuss what is sitting deep inside the atom, the nucleus, its structure, its properties, radioactivity, fission and fusion, and that should complete the course. So, thank you very much. Have a good day.